Didn't join the meeting.
So I'll send this time, Maria.
No, I said 2:20. We said 2:20. That's what we said. You think he's gonna bust in here in the next minute?
Easier.
You can only have one though. You can only buy 2 copies. Really? Did you get caught up in the toilet paper craze? Did you buy? Okay. Let's get started. Okay, so anti-differentiation is actually undoing the differentiation. Like you're given the derivative and I'm asking you to go back to the original. Yeah. So now what I've done, it's a fancy symbol. The symbol for integration is like, I call it a music symbol. I call it treble clef, and at least here to disagree with me. It just reminds me of a music symbol. No, I know. When every year somebody else me and tells me it's not true. Every year I think it's yeah, that's what she gets for everything. I get to call it a music symbol. It's not here to correct me. Okay, so that's what we're going to do today. We're going to start with the derivative, and I'm going to ask you to work backwards to the original. So this is this unit. So this one with the capital F, this is the original function. No, not your derivative. And the lowercase one in this case is your derivative. So we've lost the primes on here. So it gets a little bit confusing, but not terrible. If you just remember that the first function, the original function, the displacement function is capital and the derivative is lowercase. So a little bit different. So going back to chapter 2, if we took the derivative of this, what would we get? X squared, because the 3 would come up front, 3 divided by 3 is 1, reduce that, so this one would be X squared, so F so we would say that F prime of X is equal to X squared. And the second one? The second one's going to be the exact same thing, because what's the derivative of the constant? It's nothing. So this one would be, and again, the last one, just because it's a different constant, doesn't really change the rules of derivatives. So all 3 of these equations give you the exact same derivative. So we have a little bit of a problem. So we're going to start like basic today, and then on Monday, we're going to get a little bit more crazy with it. We're going to cancel the test for tomorrow. Okay? I don't know what I'm going to do with the test yet. I just need a moment to think about it, but we'll get through it. Totally. I'm going to be here. So if you want to get it done and over with, and you want to just see where you are, perfect. What we're trying to point out here is that derivatives are not unique. Like we can have the same derivative for 3 unique equations, right? So let's just looking at this one. What are 3 possible antiderivatives? So that would mean that this is the derivative. So that one is the derivative. So give me some original equations. original equation. So you gotta undo the deriving. Okay, so capital F of x is equal to definitely x cubed, right? But what's the constant in front of it? Has to be 1, right? Because if it was a 1 in front, we bring the 3. 3 times 1 is 3, and then we reduce that to a 2. Okay? What about this one? So plus x squared. So that could be our first one. We could just stop there because the derivative of this is that, right? So do another one. What's the thing that's going to change? Are these going to change? No. What's going to change? If there was a constant. Right? Because what's the derivative of 3? 0. So that would be the same derivative. And then, because I asked for 3, let's do 3. What can be example? Minus 2.7. Because if I take the derivative of negative 2.7, I still get a 0. This is still the derivative of that third equation. That wouldn't work for this one. It wouldn't give you a derivative of 3. So if I had 1/3 x cubed plus 1 x squared, when I do this, this would come down, and this one would be 3 over 3 x squared, like when I'm deriving it, and that would be 1x squared, or 1/3 x squared. So putting a fraction in front isn't going to give me the derivative I want, so we can't do that. Okay, determine the antiderivative. So if I'm asking for the antiderivative, that means I want the original. So I want the original function. So this would be my derivative. So what would be the original function? So capital G of t So what do I know the exponent's going to be? It's going to be 5, right? Because if I do the derivative, then I'll be down to 4. And I want a coefficient of 1. So it's going to be a fraction. What's going to be the fraction? Right? Because when I do the derivative of this, I bring the 5 down in front. 5 times 1 is 5. 5 divided by 5 goes back to 1. Okay. And then that's going to be plus something in front. T squared was definitely something in front. So I have to bring the 2 down. So what if we did this? What if we did 3 times 1/2? Because if I bring the 2 down, this will give me 1. This coefficient will give me 1. 1 times 3 is the 3 I'm looking for. Okay. We'll tidy this up in a second. Because there's more. What? So it would be 3 over 2. Yeah. Okay. So then the 5, that's in my derivative. So that's going to be definitely a t, right? 5t. But it's going to be a subtract, right? Because if I bring the 1 down, times it by 5, that'll give me the 5 down. So this would be 1 over 5t to the exponent of 5 plus 3 over 2t squared minus 5t. But there's something that we've done. Going right back up to the top. What was the thing that we didn't know? The constant had no bearing on the original function, right? We don't know if it's there or not there. So what we do when we're doing the antiderivative is we say plus a constant, plus c. So that represents an unknown constant. Because we don't know if there was a constant there or not there, because the derivative of it is going to be 0. That all makes sense? It's a little bit confusing because you got to think backwards, you can think forwards for a long time. Okay, so here's some great pictures. Integration. Integration is the process of finding the area under a function curve. Now, it's super simple when it is a nice horizontal line. What is the grade area here? So we're going to find the area. So we're going from 0 to 2. So what's the base of my rectangle? 2. What's the height of my rectangle? 3. What's the area? 6. I don't know what the units are, so we're just going to say 6 units squared. Okay. Again, when they're linear functions, it's super easy to do. We don't need integration to do it. So if we're going to do this one, I might do the rectangle. I might break this into composite, make this a composite area where I've got a rectangle and a triangle. So the area of my square now, a 2 by 2 is going to be 4. What's the area of base of 2, height of 2? Triangle. So what's my area? Okay, you guys don't need any fancy math to be able to do that. So when it gets to a curve, like in the next one, all of a sudden, it doesn't work out as nicely. So the idea is that integration does this. It takes the area of these rectangles and it approximates an area. Now, the smaller or the narrower the rectangles are, the more accurate of an approximation. You've done this with limits, right? The smaller that distance is of h, the better we're going to be able to predict. Okay, so curving functions are more difficult. So we find the area of each rectangle, and do you guys know what sigma means? To sum them, right? Like to add them all together. So this is saying that the delta x is the width of the rectangles, and you would have to calculate each height. That makes sense to everybody? Are you okay with that? We don't know the heights of this one, so this would be hard for us to do. But let's try. So A has a point at, we'll say, 1 and 0. B has a point of, what do we think? 1.5?
Yeah, sure, 1.5.
1.5 to maybe 1.75, or maybe we shouldn't do this. Right, so you would have an idea of this is a half, and we know that each width here is 0.5, right? So if we know that this is 1.75 and the width is 0.5, then we'll be able to calculate the area of this one. And then if we knew these coordinate pairs, we'd be able to calculate the area of all of them, and then we just sum them together. So that's what that sigma means, right? You guys okay with that?
Yes.
Yeah, maybe, possibly. Okay, so here's where you can do this. I gave you the table. All right. So let's go. This is your, so as you can see here, mine are much closer together. And we know, tell me anywhere? Okay, this one's for the other one, sorry. This one's for the one on the other page. So what would be the area of this rectangle if you know the width and the height? 0. what would be the area of this one? So we're just timesing this. It's really straightforward. So you're just timesing it. So this is 0.875, and this is 1.5, which makes sense. And this one is 1.875. I'm bouncing around here. 2.875. 1.5 and 0.875. Now we would expect that it's a parabola, so the areas would also have that symmetrical pattern as well, right? We would expect that. So the total area is going to be, if I add those all up, 10.5. Now that's pretty tedious, right? Did yours say rectangle in it, or does yours say triangle in it? It's supposed to be rectangle. So now we would say that going from, so this is what this means. So we're going from, these are domains. Max, and this one is a domain minimum. Nothing to do with the y's, right? So I'm saying go from 1 to 5, and our dx, that was the delta, that was, go back to the other page. It told us our delta, right? Somewhere around here it did. Here we go. Our delta is the width. So the change in x is 0.5. So what we did, and this, so we took the function times by the derivative, d of x, which was a delta, so it's going to be approximately, so two wavy lines means approximate, so that would be 10.5. So we went from an x value of 1 to an x value of 5, all the y values, and essentially we sum them all together. Okay, so in integration, we're going to be summing those rectangles. But we're going to do it a little more efficiently, because this seems like painful. But remember how we learned limits and we did the table of values first to kind of get the idea of it, and then we used the formulas? Same sort of thing. So here, we're going to get more better. We're going to get a more accurate solution. So it's telling me that the area, and I've changed my delta x, which you wouldn't know unless I told you. So now I cut those rectangles in half. So now this is 0.25, 0.25, 0.25, 0.25. So now there's 4 sections in between. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Right? So they're quarters. I mean, I guess you could figure that out doing that, but our delta now, our delta x is 0.25. And if we went even smaller, so the smaller our delta x gets, the more accurate our area is. So again, if we wanted to do this by hand, we would be calculating the areas of all of these. So if you look at your second picture, if you look at your second picture here, if this is x, can you guys see that? It's really fuzzy on left. Can you see that? If it's x, and the next line is x plus h, that means that my delta has a value of h. It's just the distance between them. So if I want to find the area of that rectangle, like area is based on height, right? Easy enough. Height we know, the f of x we're going to know, but the h, the delta is that h value is your width, or your delta x. Good times, good times. I know you're super excited. Oh, and then that's really far down on the page. That was supposed to be right underneath it. Okay, so the antiderivative f of x is the same as the integral of f of x. So they mean the same thing. The antiderivative is the same as the function describing the area under the curve. So here's your first fundamental theorem of calculus. Your original function, so it's got the capital F, is the same as the integral. So a being your minimum, x being your maximum, your derivative times by your delta t. So then we know that the derivative is equal to the integral. So they mean the exact same thing. So we're looking for derivative and the integral mean the same thing. Good first video, good first video. Okay. So if you see the integral sign, and you see f of x times d of x, you're going to undo the derivative. You're going to go back to the original. Okay, you ready for this? So this is how you do it. So the power rule, so if you want to undo a derivative, instead of minusing one, what are you going to do to the exponent? You're going to add one because you're going backwards. And then that will be your denominator. Okay? And you're always going to finish it with a plus t. Okay, y can n not equal a -1, because then it'd be 0, and then that would have a value there. It wouldn't be the derivative, then you'd have a 0, which would be very confusing. Okay, constants. These are pretty easy. We've done them before. So all you're doing with the constant, if it's with the function, you're just going to pull it outside. The k is the constant. We use it as a k because it's a scalar constant. It's what you're multiplying by. We use the letter c if we're adding it in. So k is a scalar constant. We call them when we're multiplying them. K is multiplying by just a number, like a numerical coefficient, and c is if we're adding in just a number. Okay, so we're going to antiderive this using those two rules. So this is the same thing. So if I do lowercase or f prime equals this, it means the exact same thing as this. It's saying, hey, I've already taken the derivative of this is my derivative. That's what it's telling me. All right, so let's undo it. So first term. So we're going to start with a capital F. We're going to go capital F, f of x. So what do we do to the exponent here? Add 1, so it's going to be x to the exponent 4, and the bottom is going to be 4. Pretty easy, right? So we're going to keep our subtract. What do we do to the squared? Add 1, so we're going to keep the 6. We're going to go x cubed, and we're going to divide by 3. So whatever your exponent is, that's what you're dividing by, right? Because that was an n plus 1, and this is an n plus 1. So we're going to do the exact same thing. And then I've got 1, so we're going to have, really that was 1x to the exponent 0. So we're going to add 1, which will be 1x. You can totally just put x. I'm just putting it so we see it, and I'll be dividing by 1. And then the last thing I have to add is the constant, so the plus. Which one? Oh, I missed one. Sorry, I just jumped right to the 1. Sorry. I missed that x. So the x will become x squared, and we'll be dividing by 2. This will be plus. If I can write it, I've read it. Plus 1x divided by 1 plus my c. I'm just writing that right now. Like you're going to get to the point where you can do this pretty quickly. So we're going to tidy this up. So this would be x to the exponent 4 over 4 minus 2x cubed plus x squared over 2 plus plus x plus c. I am not opposed. I'm not opposed if you like to see it like that. I'm okay with either of those. Some people like to see that 1/4 out front. I think it's easier to do it this way, but if you prefer to do it that way, that's fine as well. So that is done.